In 1949, the Canadian psychologist Donald Hebb published a landmark book titled The Organization of Behavior. At a time when psychology often treated the brain as a black box, Hebb sought to bridge the gap between abstract thought and physical biology. He proposed that our memories and behaviors are not just ethereal concepts, but are actually rooted in the physical structure of our nervous system. This shift in perspective was revolutionary because it suggested that learning is a physiological process of change. Hebb hypothesized that when we learn something new, the actual connections between our neurons undergo a transformation. This idea provided the first real biological framework for understanding how experience shapes the mind. The core of Hebb's theory is often summarized by the famous phrase, "Neurons that fire together, wire together." In more formal terms, Hebb proposed that if a neuron repeatedly or persistently takes part in firing another neuron, the efficiency of that connection increases. Imagine two neurons, A and B. If neuron A consistently contributes to the activation of neuron B, some growth process or metabolic change takes place in one or both cells. This change strengthens the bond, making it more likely that neuron A will trigger neuron B in the future. This is the fundamental mechanism of associative learning. It explains how we link concepts together, such as the smell of a rose and the visual image of its red petals, simply because those neurons were active at the same time. What makes the Hebbian rule so significant is its biological plausibility. Unlike earlier theories that relied on abstract logic, Hebb's rule described a process that could actually be observed in a laboratory. Decades after his book was published, researchers discovered a phenomenon called long-term potentiation, which provided the experimental evidence Hebb lacked in 1949. Long-term potentiation is the long-lasting increase in signal transmission between two neurons that results from stimulating them synchronously. This confirmed that the brain uses a system of synaptic plasticity to encode information. By showing that the weight of a connection is dynamic rather than fixed, Hebb gave us a map for how the brain physically rewires itself in response to the environment. Hebb's influence extends far beyond biology and into the realm of computer science. His work is the direct ancestor of the mathematical rules used to train artificial neural networks today. Specifically, the Hebbian rule paved the way for the delta rule, which is a centerpiece of machine learning. While Hebb focused on the simple strengthening of connections through simultaneous activity, the delta rule refined this by looking at the difference, or the delta, between a desired output and an actual output. Even though modern algorithms are much more complex, they still rely on that original Hebbian insight. That learning is essentially the process of adjusting the weights between interconnected units. Donald Hebb's 1949 proposal remains the cornerstone for both our understanding of human intelligence and our attempts to recreate it in machines.